split. And no, that was a complete non sequitur. But I do need to make an announcement, okay? Which is this: I travel a lot. Actually, I haven't been traveling for the last few weeks, thank goodness. But I do travel a lot through the semester. So we have to have a mechanism to make up classes. I'm sorry, okay? Now, normally what I do is I go through a very complex procedure of trying to find what time we can all meet. But unfortunately, that's not going to work, okay? And the reason is that you can't imagine how many hours I've spent trying to figure out how to get the technology and logistics of this class to work, okay? It's been a Herculean effort, okay? So there is really only one option for us, okay? Meet at 5:30 on Mondays in EE 129. So how many people... So if you can't meet at 5:30 on Mondays, let me just double check that I got the right time here. Calendar, right? So this will be Saturday, Sunday, Monday, right? Oh, there it is. Yeah, 5:30. And if you can't meet at 5:30 on Mondays, well, I mean, what you can do is you can actually just watch the videos, just like the off-campus students do, okay? And for the off-campus students, I don't think this really makes any difference. You're just going to watch the videos. It's just that it'll be available at a slightly different time. Same bat time, same bat station. So, how many people can't make it at 5:30 on Mondays? Oh, wow. You can't? You have a TA or something like that? You have some other conflict, right?
Yeah.
But you'll be okay, right?
Yeah, I mean, the class is okay.
No. The good news is this: the ECE 129 holds about, I don't know, 500 students. So just in case you have some friends that really want to hang to listen to this class, feel free to bring them along. We're going to have plenty of space. Maybe what we could do is we could play, I don't know, videos and put up some kind of like disco light. We have a little party. But it's pretty cool. Yeah, it's like this huge room. I'm like, you guys really want to give me this huge room that holds 1,000 people? And they're like, well, it's going on to have the right equipment in it, and nobody else is using it anyway. So I have it now. So good.
That's going to be this coming Monday?
Yes. We'll start with this Monday. Because basically what we'll do is, okay, so for people who know my standard mechanism, for the people on TV that have had me before, they probably don't realize this, but I have a protocol I use when I'm on campus, which is that I travel so much that I just hold 4 classes a week. And then I keep track of how many classes I've given. And if we get too far ahead, we can start dropping some of the makeup classes. But usually what happens is that, it kind of, it's sort of like a tortoise in the hare, and we sort of jump ahead and then we go behind. We jump ahead and somehow in the end we come out about right. Okay? I appreciate your flexibility on this. Good. I don't think are there any other questions or announcements or things? So let me kind of go over to the document camera then and get started. Okay, is that good? And I will say thank you, Jeff Decker, in our studio audience or whatever, for your question today. So Jeff Decker was kind enough to have a series of interesting questions, and I think I'll go through them really quickly. He had some questions about the problems which he had worked on. So let me, so thanks, Jeff. Okay. In camera. By the way, if any of the off-campus people have any problems with the audio or the video or the quality, I know it's not, it's not like maybe the super best of flow in the universe, but if you have any kind of problems, or if there's something that you think I can make a little better, please let me know, okay? Because I'm assuming if I haven't heard anything that is good enough or okay, all right? Okay, now, so Jeff had some interesting questions. actually, maybe I should do this. So today is Wednesday, the 11th, and we're supposed to be doing sections 4.3 and 4.4, which is really the next lecture. So I am just so blown away with enthusiasm that Jeff Decker actually read the notes and started working on the problems for this section that we're doing today. Because that means he's going to get more out of our lecture because he's actually going to understand what I'm talking about. So if you recall, we were talking about non-causal predictions. So we predict each pixel, the pixels both before and after it. So I'm first going to do the 1D case, and then I'm going to do the 2D case. But I'm going to warn you in advance that it's going to turn out that non-causal prediction is actually not so valuable for the 1D case. That's why you don't see it very often. Intellectually, it's interesting to go through and do the development. Okay, it all works out very beautifully. But it's not particularly useful. And the reason it's not particularly useful is because in 1D, the causal and non-causal cases work out to be parameterizations of the same family of distributions. So one may be more or less convenient, but neither is more general than the other. And I have this little Venn diagram that comes later in the chapter where I try to capture this. So you have Gaussian random processes, right? And then among all Gaussian random processes, you have things that are Pth order AR models and Pth order Gauss-Markov random fields, okay? And they're exactly equivalent. So they fall into the same grouping here. But what's going to happen is if you have a 2D AR model, then the 2D AR model actually is distinct from a 2D Gauss-Markov random field of order P. Neither of them contains the other. In fact, they have some intersection, but it's not total, okay? But it turns out a 2D AR model of order P is a special case of a 2D Gauss-Markov random field of order 2P. That just basically shows the relationship between them, okay? And the number of parameters in an order P model really increases as P squared. So you might say, well, I'll just use an AR model of order P and just make P big. I'll make it like 10 or 20. And that's good enough, right? But the problem is that that gets to be like a lot of parameters. And the other thing is this. It turns out that, okay, so I can use a Pth order AR model, and that's included within a 2P order Gauss-Markov random field, but this is more general than that. And the stuff out here that isn't included in the AR model is significant, because this AR model tends to always have a certain orientation associated with the fact that you do this causal ordering of the pixels in 1D, which is not natural. I had a long conversation with one of the students after that they were trying to think about this. So it's each one, I think what you want to get out of this chapter is that, well, first of all, there's some technical machinery you want to be able to manipulate, okay? But then you also want to understand that each approach has its strengths and its weaknesses. There's no complete solution that's totally satisfying in all ways, right? So when you go to the causal structure has certain analytical advantages. In particular, the matrix is lower triangular, so the determinant transformation is simple, and that has certain advantages. We'll find out later in parameter estimation and so forth. But the disadvantage of it is that it's not so general, okay? So the advantage of the non-causal one is it's more general, but the disadvantage is it's not as expressive, okay? So, this is 56. Okay, so now, so this is the model, and then basically what happens is that, okay, you have Now the prediction error, the predictor is non-causal. I have this notation here. I say like that little partial symbol of n, that means the neighbors of n. Now one thing that's very important, okay, and maybe I kind of skimmed over it, but you've read the notes really carefully, right, is that this neighborhood relationship has to have the following properties, okay, that, where do I define? Okay, hold on. Blah, 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 blah. Okay, okay. Let me just get a tablet and I'll write it down. This is actually a very important concept, what I'm about to say, which is neighborhood. So you have neighbors, okay? So in 1D, you had this idea of the causal relationship, but the causal relationship is asymmetric. So if you have, so if this guy, okay, is a pixel in question, and say these are the pixels mirroring. So let's say these two pixels are neighbors of that pixel, right? That pixel is dependent upon its neighbors, right? So we say that, so this is the pixel F, okay? And then we have partial F, these are the neighbors of F. So that's a set, right? So that's a subset of all the pixels, F, okay? And in this particular case, the neighbors of F is equal to the set F minus 1 and F plus 1, right? Simple enough. Okay, now, the neighborhood relation has to have this following property, that if R is a neighbor of F, then F must be a neighbor of R, okay? And furthermore, F can never be a neighbor of itself, okay? So those are important properties. So it has to have this symmetry relationship. Now when we had causal neighbors, so let's say this is the point, and we only had this kind of relationship, where the point before it was neighbor, sort of. I didn't use the word neighbor, actually, but it had this relationship, right? That is not a symmetric relationship. So in that case, if this is, say, R, and that's F, then R is a neighbor of F, but F is not a neighbor of R. Now, what I'm saying there is not correct, because the word neighbor I will carefully use only to mean relationships that are symmetric, okay? So I'm using the word neighbor here incorrectly, informally, because, you know, it's sort of natural, okay? But I wouldn't write it in the notes, okay? So that is a key difference that makes the causal and the non-causal cases different, okay? So, yeah, so you got to keep that in mind. It's very important. Let's see. Okay, so now what happens is you can write down the distribution, and B here is by definition the inverse covariance matrix of the distribution. So we call it the precision matrix. And we know that the conditional distribution of a pixel given all the other pixels has to have this following form. Okay, because we know that the conditional expectation of the pixel given the other pixels has to be a linear function, and this is a general linear function. I'm assuming everything zero means, so since it's zero means, it has to be a general linear function without a constant. And whatever the prediction variance is, I'm just saying it's sigma n. That's definitionally it, okay? So it's got to have this form. So I can relate these two things. I can take derivatives and set things equal, and I can relate B to the sigma and G, and I can relate sigma and G to B. So we have basically two different parameterizations of the problem. So one parameterization is that you have B, okay? And the other parameterization is that you have sigma n squared for every n, and you have Gn, which is the prediction coefficient, okay? So this is, I'll call this Bij. Okay, so that's one set of parameters, and this is the other set of parameters. They're equivalent. Well, okay, I know this completely parameterizes the distribution, B's, and it seems like maybe if I knew all the sigmas and the g's, that should be enough to get the b's. But certainly the b's have to tell me the sigmas and the g's, right? Because if I know the joint distribution of everything, I certainly should be able to compute calculate the conditional distribution. But it turns out that there's a direct relationship between these two, okay? So I can actually parameterize this in the finite dimensional case by a matrix B, okay? And then the sigmas here I'm going to write as lambda, okay? And, oh no, it's not writing as lambda, I'm sorry. Okay. I should look at my own notation. I use the variable gamma, that's a diagonal matrix. And this I call G, okay? So there's a relationship between B, the matrix B, okay, and these two matrices where this is diagonal. Gamma is diagonal and G is a full matrix, okay? And if I start differentiating and set up equalities, it turns out that the relationship is this, that this gamma matrix is the diagonal. It's the diagonal of B inverse. It's not the diagonal of B inverse. Okay? Oh, okay. Those words, okay. I just said something that was like a self-contradiction. I said, it's the diagonal of B inverse. It's not the diagonal of B inverse. Okay? So I basically said P and not P. Okay? Okay? So, okay, let me try to say it a little more clearly, okay? It's the inverse of the quantity of the diagonal of B. The diagonal of B is a matrix, and I take its inverse. It's a diagonal matrix, and I take its inverse. It's not the diagonal of the matrix inverse of B, okay? So it's the order of operation. Now, G, then, is really just the off-diagonal of B, but it's an easy enough way to write that. It's actually 1 minus the off-diagonal of B. So the easy way of writing that is just to write that G is the identity minus, you take gamma times B. Okay, actually that's not entirely true. So it's related to the off-diagonal. This is the formula that's correct, okay? This formula is correct. What I said before isn't quite correct. I mean, if gamma is 1, if the prediction variances are 1, then, or if they're a constant, right, then the G's are just the negatives of the off-diagonal elements of B times the constant, right? So that's the relationship, okay? So from this, if gamma in general is the G a symmetric matrix, well, not necessarily. B is always a symmetric matrix because it's the inverse covariance. It's also got to be a positive definite matrix, right? Because it's the inverse of the covariance matrix, which is a positive definite matrix. So, but G is not necessarily symmetric. It's only symmetric if, say, in special cases. It's symmetric if this gamma matrix is, say, the identity times a constant, right? Because then this would be just times a constant. So, if the prediction variances are constant for all samples, then the prediction coefficients will be symmetric. But if they're not, if it's not constant, if it's space varying or time varying, then it won't be symmetric. Okay.
What do you mean by prediction coefficients?
The prediction coefficients are the G's.
Okay, G's.
Right? Because.
Okay.
Because. Yeah, here, those are the coefficients that you multiply the samples by and add them together to get the prediction of the current value, right? So the G's are the non-causal prediction coefficients. The B is the precision matrix, and the gamma here is the inverse. Oh no, the gamma is the actual prediction variances. The gamma is the diagonal matrix of prediction variances. Of non-causal prediction variances, okay? All right? Now, and then I go through some more stuff here. Jeff made the point where he was like wondering why it was that that this expression is zero. The expectation of En times xi is zero. Well, it's zero as long as I is not equal to n, okay? Because, and I is never equal to n, because when I equals n here, then the corresponding value of g is zero. So g at zero is zero, right? Because you can't use the current value to predict itself or you'll get a perfect answer, right? So the prediction coefficient at zero is always zero, right? You've got to ignore your current value or the problem would be too easy, right? Everybody see that? So the g at the current value has got to be zero, otherwise you'd be cheating, right? So you can't use that. So xi is always going to be different than xn. So this is page 60. The middle, there's three equations in the middle of the page, and this is the center of the three. And then, so you're using x to predict e, right? So it's got to, so the prediction error has to be independent of everything you use to predict it. That's property 4.1. So that's how you know that this is going to be zero, okay?
So how come the error at n is independent of all the other random variables, but all the other errors are uncorrelated this time? I mean,
the prediction errors are not uncorrelated in non-causal cases.
Yeah, I know.
Yeah.
And how come is that possible? Because the prediction errors at n is basically independent of all the random variables, but the prediction errors are correlated. Why is that so?
Because it's true. So it's like one of those things. I mean, I'm not making fun of you. Okay, the problem with this class or this material in general tends to be that people will go, "Gee, why is that true?" Okay, there's only certain answers I can give to that question. One is some technical proof. Okay, but somehow that's not satisfying. You're looking for some deeper insight. Okay, so then we sort of venture into the realm of the subjective, and I can try to do my best, but I may or not be able to offer you a satisfying answer, okay? So I'll try my best, okay? But what happens is that, okay, the x's are being used to predict e's of n. So anything I use in the prediction, it's got to be independent of, because if it wasn't, I could do a better job of predicting, okay? But that doesn't mean that the different prediction errors are independent of each other, because, say, e of n plus 1 used en to predict it. See, in other words, there's a so-called looping dependency, okay? So loopiness isn't just a property of faculty. It also can be a property of a graph, okay? So you have nodes in a graph, okay? If you have a directed acyclic graph, then it turns out that you have a directed graph and each node points to some other node, right? Like this, okay? That's a directed acyclic graph because there's no cycle. If I start here, I can go there, but then I stop. If I have two nodes like this, that's called a loopy graph, okay? Because there's a cycle of dependency. And the problem in the non-causal prediction is you have cycles of dependency. That's really a very fundamental concept that you will eventually realize underpins a lot of what we talk about in this class. And there's entire other fields of research that are essentially equivalent to what I'm going to teach in this class, okay? It's called things like belief networks. Belief networks. Belief networks talk about things like you can have acyclic belief networks, or you can have trees, or you can have loopy networks. Loopy belief networks are just Markov-random fields. Okay, so that's another reason why we're really interested in Markov-random fields, because it really is. I'm sort of tricking you into leading you down this path of learning about something that's kind of fundamental. Okay. At least that's my hope. Okay? Now, now what happens is now if you you can look at the special case where you assume that the prediction errors are not a function of time. If they're not a function of time, then it's easy to derive, and you should definitely derive, and it could easily be on an exam, and it's right in the notes. All you have to do is reproduce the proofs I have right here. So this is not just reading the notes carefully. Is that, well, what's the autocorrelation of the prediction errors in the, what's the autocorrelation of the prediction errors when you have causal prediction? Everybody should know the answer to this. If you have a causal predictor, what's the autocorrelation of the prediction error?
The autocorrelation of the input function.
What did you say? Everybody said the same thing, right? Okay, everybody said that the autocorrelation is going to be a delta function, right, times the constant, right? Good. So you guys all know that. And then what's the power spectrum? How do you calculate the power spectrum of a random process if you know it's autocorrelation? You have a stationary random process and you know it's autocorrelation. How do you compute its power spectrum? You take the Fourier transform. So for discrete time random process, more specifically, you take the discrete time Fourier transform, right? By the way, I don't want to burst anyone's bubble or ruin, okay. Tooth fairies really exist, okay? But the thing is this, that there actually is no such thing as a discrete time Fourier transform. If you look at it and blink your eyes, you'll realize the discrete time Fourier transform is just the inverse Fourier series. Oh no! It's like, I don't know if you've ever noticed this, but Twinkle Twinkle Little Star and the ABC song are the same. It's like, twinkle, twinkle, little star, how I want, and the same thing, A, B, C, D, E, F, G. I was devastated when I found that out, okay? So, it's the same thing with the discrete time Fourier transform and the inverse Fourier series. They're the same transform, okay? Oh no! It's true, I'm sorry. So, no one actually, So the discrete time Fourier transform is just a figment of the signal processing communities of imagination, okay? But nonetheless, it's quite useful, okay? So, all right. So, okay, so you got this? So now that's the time autocorrelation of the prediction errors for the non-causal case, right? And it's just delta of n minus the prediction filter, okay? Times a constant having to do with the non-causal prediction error. So let me just see what that looks like. Okay? So what it means that, so remember you had the signal, right? And you had you had coefficients and you added them together to predict this guy here, right? So you have so you have the center point and it's 1. You always multiply by 1 because you take that pixel, right? And then over here you say minus g of minus 1, right? And you have minus g of minus 2, right? Or whatever, dot, dot, dot. And over here you have minus g of minus 1, or you could make this plus 1. It's going to be a symmetric function if it's a stationary random process. And this is minus g of plus 2. So in a special case, right, a special case of interest in the notes, okay, you get something like 1 in the center and you get minus 1/2 and minus 1/2. So that's your prediction filter, okay? Now it's actually slightly a lie if you caught me in a technical error, okay, which is that this is actually not a valid non-causal predictor. Okay, for reasons I'll explain later, but it's actually very close. It's asymptotically close to something that's valid, because if this would have a power spectral density that went to infinity at 0, okay, but don't worry about that little detail. I mean, what's plus and minus infinity among friends, right? So, I mean, the thing is that, so you just have this little thing, okay, but basically you take the two neighbors on either side and you average them and subtract it from the center point, and that's your prediction error, okay? So you take this function here, you take its Fourier transform, so you take the discrete time Fourier transform, And that's going to be 1 minus g of omega, which is going to equal h of omega, or maybe that's I'm going to call it f sub epsilon of omega. So it's the power spectrum of the prediction errors. So the power spectrum of the prediction errors is 1 minus the Fourier transform of the prediction filter. So in this case, you could calculate it, right? Actually, if you calculate it, this looks like something like, oh no, I'm sorry, it's over that, oh my God, I gave you the wrong answer. So it's divided, it's 1 over that, so it's times sigma squared NC, okay? Okay, so you guys are really smart, so you knew I made that mistake, right? So you were just being polite by not pointing it out. So you can calculate this for like a simple example like this is something like the power spectrum of the prediction error is just going to be something like non-causal squared, sigma non-causal squared over 1 minus something like 1/2 cosine of omega, something like that. Actually, that might not be the correct answer, but it's something close. If you've ever done the Fourier transform, it's kind of a function. It looks like that, right? Okay? And this thing here is going to be greater than or equal to 0, right? Or this is a problem. Now, it's actually a problem because, this isn't times 1/2. This is times cosine. So at 0, cosine is 1, right? So this is 1 over 0, so that would be a problem because it goes to infinity. So the power spectrum is infinite in that case. Yeah?
Right, now, aren't you calculating the power spectrum of the random process, not the errors?
Right now, oh yes, you're right. Yes, I got this mixed up. Okay, right. Yeah, yes. Thank you. You read the notes. Okay. Yes, very good. So this is the power spectrum of the errors. That's why I got myself confused. So 1 over that is the power spectrum of the random process Okay, let me just write it down again. Okay? So the power spectrum, S epsilon of omega, the power spectrum of the errors is going to be equal to sigma non-causal squared times 1 minus g of omega. Okay? And the power spectrum of the actual random process is going to be equal to sigma non-causal squared over 1 minus g of omega. Right? Okay. So it's actually kind of interesting because they're inversely related, the power spectrum. So the process of non-causal prediction doesn't just whiten the power spectrum. It sort of goes too far, and it actually inverts. Because if it just whitened it, it would make its power spectrum 1, constant. But it actually makes it go too far. And it causes the power spectrum to be inverted. Is that clear? And you can just go through this and make sure you understand this on page 61. Okay? Now, let's see. Okay, and this is just what I just wrote down. This is equation 4.11 and 4.12. And now what can happen is that you can do the same thing in 2D. So if you go to 2D, pretty much everything's the same, oddly enough. What happens now is that you can form an image as a raster ordering of the pixels in the image. Okay, that's what this equation at the top of page 62 is. And now what happens is that, it's kind of beautiful. The reason I use this notation that doesn't, I avoid a lot of boldface and subscripts and little arrows on top of things, because if you just use very plain notation, then the same notation works in 1 and 2D. Because now we define these are sets of pixels in 2D for the neighborhood, and everything looks exactly the same. It's actually kind of beautiful the way it works out. And when we order everything as matrices, it all works the same way, right? And all the equations are the same. The only thing is now the power spectrums are functions of two variables. One is mu and the other one is mu. So one's frequency along the horizontal direction and the one's frequency along the vertical direction. But otherwise, it's the same thing, right? And now, if you look at figure 4.2, this shows the neighborhood relationship for 1 and 2D signals. When I say it's a pth order signal, so I mean you take p points before and p points after. So in 2D, it means you take a p by p neighborhood. Actually, you take a 2p plus 1 by 2p plus 1 neighborhood. So as p gets larger in 2D, the number of neighbors increases as the square of p. So, you know, you got to be careful. Even p equals 2, it starts to get pretty big. That's a 5 by 5 neighborhood, which has 24 neighbors, right? 25 points, and one of the points is the center point, so it's 24 neighbors, right? There's a lot of neighbors. Now, in this table 4.1, I actually wrote out the relationship between the 1 and 2, the 1D AR and Gauss-Markov-Random field models and 2D AR and Gauss-Markov-Random field models. And there's relationships in both time and frequency, okay? So we have the model parameter, we have the space autocorrelation relationship, and we have the power spectrum relationship, okay? So now you can ask yourself, well, when can one model express the same distribution as the other model? And it turns out, it's not obvious really, but in 1D, it's a classic result that this comes out in like Paley-Wiener theory, and it comes up a lot in like optimal control problems or so forth. Like when you want to, it used to be that we taught Wiener filters as analytical filters, where you'd actually do spectral factorization to find the optimal minimum mean square error filter that would give you some output that was constrained to be causal. We don't really teach that material. You have to do the spectral factorization stuff. We don't teach that material much anymore because it's kind of interesting, but it's not maybe used as much as it did because now you can do things on computers, okay? But those theorems, basically, it's a classic result, which is that you can find so in this table, the top table 4.1 under the power spectrum, we have two different expressions for the power spectrum. One for the 1D non-causal and one for Gauss-Markov-Random field, the other one for the causal AR model. And the question is, well, can I find a causal filter which will make the two power spectrums equal? And the answer is in 1D you can. You can always do it. You can always find an order P predictor which will give you exactly the same power spectrum as the order P non-causal predictor. It's really quite surprising. It's related to the fact that you can always factor a 1D polynomial. So in 1D, you have the fundamental theorem of algebra, right? And if you have an nth order polynomial in one dimension, you can always find n roots to it. This is like what high school algebra, right? Quadratic equation always has 2 roots. But in 2D, that's not true. You can't always find roots. So therefore, you can't always factor the polynomial, and that's all related to the fact that you can't necessarily find a causal predictor which gives you the same power spectrum as the non-causal one in 2D. In 1D, yes. In 2D, no. Okay? So that's basically what this is all saying. Property 4.2 kind of states that. Okay, now what happens is if you go to 4.3, figure 4.3, here I show the relationship. You have a 1D AR model neighborhood and 1D Gauss-Markov-Random field, okay? And now you have below that, so that's not so interesting. So if you take the 1D model, you can calculate the autocorrelation for the 1D case, okay? Okay, so basically, if you look at this equation, this example 4.1, I assume that I have an AR model, a first-order AR model. This is just like the homework problem, okay? And now you say, well, what's the autocorrelation function associated with the non-causal, with the random process? I can calculate the autocorrelation of the random process. Well, I can actually calculate the actual non-causal prediction filter because I have this equation, which is the equation in table 4.1. I basically can equate these two expressions to the autocorrelation, right? And let me see, where is that? This is 65. So, let's see. So, you write down, okay, so you write down you equate the two expressions. Oh, here it is. So it's equation 4.13. On the left-hand side, I have the autocorrelation I would get from the causal predictor, and on the right hand, I have the autocorrelation I get for the non-causal predictor. So if the two models are same, right, then the two autocorrelations should be the same, right? That's not entirely true. I'm lying slightly here. This equation is correct, okay, but it requires a little bit of a derivation because read the notes, okay? But equation 4.13 has to hold if the two models, the causal and the non-causal models, are the same, okay? Read it, okay? Because the power spectrum of the random process is actually the inverse of this Fourier transform, okay? But if the inverse of the Fourier transform is equal, then the Fourier transforms have to be equal, right? Okay, so these two equations have to equate. Now, if I pick a Z, I may not be able to find an H that makes this true. Because here I have H, and then I'm convolving with this time reverse. So that's the correlation. So the autocorrelation of a function with itself, in general, if I find a G, I may not be able to find a function whose autocorrelation with itself equals that function, right? You know, we can talk about this some more, but essentially what I'm doing is like I'm taking the power spectrum and taking its square root. The square root of the power spectrum may not be a rational function. Usually it's not, okay? Sometimes it is, but most of the time it's not. But if I take a causal filter, and I do the autocorrelation of the causal filter with itself, I'll get something, and it'll be a symmetric function, and the associated G's will be the non-causal prediction filter. So if I have a causal filter, I can always easily find the non-causal predictor. If I have the non-causal predictor in 1D, it turns out there's a theorem which says that the causal predictor exists, but it's a little complicated to calculate. And in 2D, it doesn't exist. Okay? So, problem 4.1 is just working in an example. You've got to read the example 4.1. It's not that complicated if you do it step by step. And you'll understand that we calculate from that the actual autocorrelation prediction filters. Right? And it turns out that the interesting thing here, if you look at the figure 4.3, is that if you have this causal predictor, you might think that a PS order causal predictor would produce a PS order non-causal window, but it doesn't, because this shape of this prediction window is sort of asymmetric because of this crazy raster ordering, right? You get this sort of weird, I don't even know how to describe the shape. Does anybody have a name to describe the shape? Like, I don't know, it's kind of shaped like a, it kind of reminds me, there's that puzzle where you take the pieces and you have to try to stack them together. Does anybody know the name of that puzzle? My wife loves that thing. Where you got like these pieces and you have to try to fit them into the spaces, right? And they fit together. Jigsaw puzzle? It's not it's like something like Tetris or something like that? Okay, we're probably violating some copyright laws or something now, which I'm delighted to do. So, okay, that's your homework assignment for next class. Find out the name of that puzzle, okay? So now what happens is, because that puzzle pieces are asymmetric, we can autocorrelate them with themselves. You get this kind of weirdly shaped asymmetric window in the non-causal domain with like little bumped holes in it on the corners, okay? So it's kind of this little funky thing, okay? And it's wider than it's tall, too, right? But whatever, that's what you get. Now, there's kind of some interesting things. There's a homework problem in here that I just find a little perverse and interesting. You might just find it unpleasant, but which is that, okay, the number of degrees, you can calculate the number of degrees of freedom in this model, right? The number of degrees of freedom is going to be the number of prediction coefficients, right, plus 1, because you have the variance. And what are the number of degrees of freedom here? Well, this non-causal predictor has to be symmetric. But if you sum up all if you count the number of dots in the non-causal case and divide it basically by 2, it's more than the number of dots in the causal case. So actually, when you go from one to the other, it's not a one-to-one mapping, because there's more degrees of freedom in one case than there is in the other. So what that tells you is a very interesting result, which is that in 1D, there's this so-called condition, which is that all AR models correspond to a P-th order correlation. So I don't know if there's any people here that are into like antenna beamforming and these kinds of problems, where there's very classic theorems that everybody knows that if you have 3 autocorrelation lags, you can get uniquely 3 AR coefficients. In 2D, that's not true. And that's the basis, that sort of lemma is the basis of the theorem that all AR models are stable in 1D. That theorem does not hold, and in 2D, all AR models are not stable. In practice, they almost always are. But in principle theory, they don't necessarily have to be. You could come up with a counterexample and make up a data set and get an unstable case, okay? This is an interesting thing. You know, I'm not sure how practical value it has, but it's just curious, okay? It's an example of the fact that in 2D, things can be really different. So, okay. Now this last chapter, 6.4, this is the completely general case. See, I'm talking about this thing being like a 2D image, okay? But it really doesn't have to be. This can be a graph, okay? That's why everything I'm teaching here is basically the same as what you learn with belief networks. So when you have a marker in the field, the relationship between the nodes is symmetric. So it's like it's an undirected graph, okay? So it's an undirected graph, and you have connections, and the connections represent neighborhood relations, okay? And it can be like this, okay? And now you can characterize it with non-causal prediction, and that non-causal predictor will impose a covariance. So you can use this to model the distribution of pixels on a graph, okay? So we have this idea of pairwise clicks. A click is a pair of pixels which are neighbors of each other, okay? So are these 2 points clicks that are not? No, because there isn't an edge between them. 2 points are only clicks if they have an edge between them. So, okay, and then, well, the theory all works out, okay? Everything we did was really general, we just didn't notice it when we were doing it, okay? So, there was, so you can write down these relationships. The G's are related to the B's, the B's are related to the G's. Life is good. It's the same equations we had before, because we really made no assumptions. We just thought we were making the assumptions when we were fooling ourselves at the time. It was really just a general graph. Everything we did worked for a general graph. We'll come back to this later, and it's really handy for lots of applications where your data may not live on a 2D array or a 1D array. Actually, the machine learning people go nuts about this stuff. They love it. So, okay, now I got 1 minute left, and good old Jeff Decker is a nice guy, and then he just good questions. I'm going to point out over here that he has some interesting questions. Is G a symmetric function? Well, the answer is it is if the thing's stationary, because the equation G was related to B, right? You have this equation right here, so if that gamma is a constant, then the Z has to be symmetric because B is symmetric, right? Okay. Does the sum of the G's have to be less than 1? Yes. Because you know what? 1 minus G, the power spectrum 1 minus G has to be greater than 0 because it has the power spectrum. Energy can't be negative. So therefore, yes, the sum of the G's has to be less than 1. What do we know about the G of omega? Well, the G of omega is a real valued function. It's got to be greater than 1, and it's got to be less than 1 and greater than 0. because the power spectrums of the signal and the prediction errors have to be positive. Okay? So I did that really fast, and then I'm going to just say goodbye to you if I come on. Okay, it was good seeing you. Bye. Good.